Hi there, I'm Bogdan. I'm a senior at the University of Michigan studying computer science with a minor in math. And today I'd like to take a few moments to share with you my Capstone project, which I did for the Engineering Honors Program. In this project, I developed an implementation of a key-homomorphic pseudo-random function in the Haskell programming language. And I was advised by two wonderful professors, Chris Pikert and Mahdi Cheragchi. To start off, let's talk about the future of cryptography, which is closely tied to the future of quantum computing. In 1994 already, Peter Shor devised an efficient quantum algorithm for solving integer factoring and the discrete log problems, which are the two problems that form the foundation of all modern cryptography today. Now, actually building a quantum computer is a significant engineering challenge. Only last year, in 2019, did Google claim quantum supremacy, meaning they solved a problem on a quantum computer that was proved to be intractable using a classical computer. There's still more hype than reality surrounding that. Experts say that we're still 20 years away from quantum computers being powerful enough to threaten modern cryptographic systems. But this is a big warning flag telling us that we need to develop robust post-quantum cryptographic systems in the next 20 years. One way of achieving post-quantum cryptography is using a mathematical object called an algebraic lattice. A lattice is just a discrete array of points over multiple dimensions. Now, there are several computational problems associated with lattices that even quantum computers can't solve efficiently. This image shows only 2 dimensions, so you might be able to eyeball some of these, but in real systems use 500 dimensions or more, and so it gets really complicated really fast. Another cool security property that cryptographers like a lot these days is called homomorphic encryption. This allows untrusted parties to perform computations on encrypted data. This is really important in applications where the data has to remain confidential, for example in the financial and the medical realms. It also allows us to use machine learning to process huge pools of encrypted data using neural networks, for example, and also allows for the decentralization of key distribution centers so that all of the secret key material isn't stored on one server. So now let's transition into my project in which I aim to implement a key-homomorphic pseudo-random function, or PRF, in Haskell. So the key-homomorphic property gives us the relation that f of s plus t is equal to f of s plus f of t, with a small error due to rounding. A PRF is a building block that provides security guarantees for many later cryptographic applications. Now, my advisor Chris actually developed the theory for a KH-PRF, but remember that we have to deploy Lattice crypto in the next 20 years, and so this project represents a first step into converting that theory into practice. The reason we use Haskell is for its rich type system. In particular, it allows us to define what are called Singleton types, or types that can take on exactly one value. This is really powerful because if you have a wrong value at any spot, instead of going unnoticed, it'll throw a compilation error. So normally a programmer would have to spend lots of time developing a complete test suite to catch all the possible corner cases. But with Singleton types, the compiler is checking for correctness, and that's a lot more reliable. In the KH-PRF program, we define singleton types for a full binary tree, which is a binary tree where each node has either 0 children, in which case it's a leaf, or 2 children, in which case it's an internal node. Each different tree topology is represented by a different type in Haskell. In our application, full binary trees are used to store states, which is used in the stateful computation of our key-homomorphic PRF. They have a special property such that we only have to update the state corresponding to nodes on paths between the root of the tree and the leaves of the tree that change. The leaves on the tree correspond to the input to the PRF, and so if we only change the input by 1 bit, then we only have to change one path in the tree, which is 4 out of the 15 nodes that we see here. So if we can enumerate all the possible inputs in an efficient way, then we would have to make very little changes to the state. We can do this using a gray code, where we can iterate through all n-bit strings, changing 1 bit at a time. Let's take a look at the Haskell code that I wrote to update the state. In this first part, we have what's called the function signature. It has multiple components. we have 4 input parameters here, 1 output type, and then since we use some of the more advanced type features in Haskell, we also have several type constraints here on top. The second part of this code is called the function definition, where the part that actually does the work. Here we're doing casework on the tree topology, T. If the tree topology is just a single leaf, then we select one of the 2 public parameters appropriately, A1 if the input bit is 1 and A0 if the input bit is 0. Otherwise, we go enter this third case and we call update state recursively on each of the left and right subtrees. However, there's an optimization that we can make if the input string hasn't changed. Because if the input string hasn't changed, then the underlying state won't change either. So we can just output the same state that we got as the input. And so that's what these 2 lines do here. Now let's see how our PRF maintains state across multiple calls. So here we have the Haskell code for that. As a reminder, here are the 4 input parameters. So we have T is the tree topology, P are public parameters, S is the secret key, and X is the input to the PRF. On this first line, we get the state that existed previously. On the second line, we update that state using the previous state. If the previous state doesn't exist, then this maybe function will essentially let us start from scratch. After we get the updated state, we call put on the new state, so in order to save the new state, and then we return the output of the PRF computation, which is expressed pretty simply here mathematically. We take S as the secret key and then multiply it by the matrix representation of the state, and then do some rounding from the integers mod q to the integers mod p. In terms of next steps for this project, it would be nice to do some more benchmarking work, because a lot of Lattice cryptography applications aren't ready for production yet. They're slow, inefficient, and they need large key sizes in order to attain realistic security guarantees for real-world purposes. We started some benchmarking work for trees with 32 leaves and various tree topologies. So we started with like a left spine tree, which is a tree with only left children, a right spine tree, which is a tree with only right children, a complete binary tree, which is completely balanced, so if you take the mirror image, it'll look the same. The reason we do this is because there are different degrees of parallelism possible on each of these different topologies, but it would be nice to do some more robust work in this regard. I'd like to thank at least a few people for helping me through this honors experience. First, I'd like to thank Chris, who was my research advisor over my sophomore summer when I started learning about Haskell. I'd also like to thank Mahdi, who stepped into the official advising role when Chris went on sabbatical. I'd especially like to thank Rachel, my honors advisor, for her kindness in listening to me as my plans shifted throughout college. Of course, my parents for their never-ending encouragement and their unconditional love towards me. And most importantly, glory be to God for his patience and loving kindness. Thanks for listening. I'd like to take a few moments now to answer some questions that other honors students might have. So the first question you might have is, what inspired me to get involved with this project? Well, even ever since middle school and through high school and even in college, I've always loved math. And I've sought out classes that look at more discrete topics, so things like algebra and combinatorics especially. And then with this project specifically, my advisor was actually my professor for EECS 376. And so that opened the door to start on this project. Another question you might have is, how have my other experiences at Michigan related to my capstone? The biggest extracurricular I was involved in was teaching. I taught as an IA for 5 semesters here in theoretical and computer science courses. And there's a quote from Albert Einstein that I really like. He said that you only really understand something when you can explain it in simple terms that everyone else can also understand. I think it's important that we don't keep our knowledge to ourselves, but that we try to share that knowledge with the wider community for its benefit. I also had an experience the first time I taught the Introduction to Cryptography course here. I had to learn a lot of the material on the fly along with the students. And so that sort of served as the intersection between teaching and research, because research is a lot about learning on the fly as well. A final question you might ask is there anything that I didn't have time for in this project that I wish I could have explored more? So I mentioned writing more benchmarks earlier, but on the softer side, I'd like to explore more of the moral side of cryptography. I think it's important to understand where the sources of academic funding come from, because that impacts the projects that are done. I think it's important that we are cognizant that our academic work is benefiting the community in a tangible, positive way. Okay, thanks for listening, and I wish you all good health and good strength during these trying times. Thanks.